you hear me? Yeah. Yes. Okay, so good morning. Thank you for coming to talk, and thank you very much for the invitation to this interesting conference. At least what I hope will be an interesting conference. Let's not jump the gun. So, how does this work? Right. So I was asked to provide a review of M2’s, and then I was asked to provide, I guess, a review on M5’s. Of course, we don't know anything about M5, there's nothing to review on M5’s. So I'm going to talk about M5’s ad nausea, and do my best to inspire about what the difficulties are, and perhaps where some avenues of hope might be, or interest. And then I'd also decided that everybody else gets to talk about research, so if we get a chance, I'm going to throw in a research talk at the end. Because I've got some research, which I was hoping to share with this community, because maybe you have some ideas about it. So if only briefly, I will hopefully mention that stuff. So a little bit of a caveat, because this is a big industry, that's not the M2, the M5s. So what I will discuss are aspects of M5’s, and because of the nature of this conference, I want to emphasize the role of so-called triage. And then I'm going to discuss M5’s, but when I talk about M5’s, I talk about M5’s mainly with a view to actually constructing or somehow handling this famous 2,0 theory in 6 dimensions. There's a lot of things that are associated with M5’s in the 2,0 theory that I will not discuss. So one of them is this huge class of literature. It's very interesting, but you've got the wrong guy if you want to have a review on this, which is about how you reduce to 4 dimensions on various Riemann surfaces, functional Riemann surfaces, etc. And you get various novel non-Lagrangian CFTs. And there's a beautiful story there, AGT, the role of surface operators, and the guy you shouldn't invite there would be Gayato. Or Gukov could be. He's coming, I think, at some point. So that will not be me. And then also, there are starting to be some bootstrap results, and these are very interesting, actually. But again, I'm not the guy, perhaps Bolt and Reese would have been the guy, he's the local. So I will not discuss those, and of course, it's very hard to go to a theoretical physics talk these days and not have ADS-CFT, and we will achieve that today. We will not talk about ADS-CFT, and again, Arthur and Paul have done some work on it recently, and there's also Chester and Homeler. So these are ADS-C approaches to the 2.0 theory. For my mind, one of the challenges of 2.0 theory is it's a challenge about quantum field theory. It all comes from M theory and string theory and all this hoopla. But at the end of the day, it's a statement about quantum field theory. And quantum field theory is something that many scientists use. And they may not have any attachment to string theory or M theory. But they certainly do love and appreciate quantum field theory. And this is something that we can teach them, impart to them, impress them with. Because if we can explain these results about 2.0 in CFT quantum field theory language, without always saying, well, string theory is M theory, it's embedded in 11 dimensions, you shouldn't need to do that. If it's a quantum field theory, you should be able to construct it. I don't mean like rigorous axiomatic constructivist quantum field theory, but you should be able to have something that any student of quantum field theory, for which there are many, can understand. And that's more of the language which I've proposed to discuss this with you. So, the executive summary of my talk, or as I call it, the Gong Show version, so you can go back to sleep, you just have to stay asleep for the 1 minute, which is, I'd say M2’s are quite well understood. We have actions. But they're intricate. They're not, just because you've written down the action does not mean that things are as simple as you might have expected. With M-Branes, you have an action, always did. The action has classical limits, and in those classical limits, you can sort of see what's going on, and the intuition works, and boom, everything's okay. The M2’s have actions. They're still strongly coupled, at least at the most interesting points, which you might want to study them. And then it's not clear at all that just having the action helps you that much. I mean, because it's strongly coupled, And there are operators in the theory which are what are called quantum operators, which means that they're not necessarily part of classical theory, and they play a very important role. Okay, the second bullet point on show is that M5 are hard and they're not well understood. That doesn't require much explanation. And the third point would be that I think there is more to explore in terms of M5s and M2s and the relationships between them, and hopefully the mathematical structures that would be useful or important there. Okay. So, any questions about my intro? Okay. Shouldn't be. All right. So let's start. And I also apologize because I don't know how much, what pace and what's known and what's useful and what's not. So feel free to ask questions, as long as you don't mind if I can't answer them. And feel free to speak me out too if you think, look, okay, that's not interesting. Okay. So formally, one could say that the M2 SCFT is the superconformal field theory. It arises as the strong coupling limit of n D2 branes. So M theory, one definition, is that it's non-perturbative 2A string theory, let's say. It's 2A string theory in the limit of large G string coupling constant, which happens to have a low energy effective action that's 11-dimensional, described by 11-dimensional supergravity. And that supergravity theory has in it two types of brane objects, M2 branes and M5 branes. And the standard dictionary is that the M2 brane is the strong coupling lift of the D2 brane. So in other words, it's the M2 brane SCFT is the strong coupling, that's wrong, IR fixed point of 3D maximal super. So MSYM means maximum symmetric, supersymmetric Yang-Mills. You'll see that throughout. In fact, when I say Yang-Mills, I mean maximum supersymmetric. I certainly don't mean the standard model. And that should be IR fixed point.
Why do you have n up there? N equals 1.
Well, so these are objects, and you can take many of them, as many as you like.
Okay, sure, but if you, okay. But then you have a pile of M2 brane.
Yeah, then you have a pile of n of them. And the idea is that the physics comes from the interactions between those n. They move, and they shift. What you're doing in all of these brane stories is you have a bunch of branes, n of them, that are parallel. And in D branes, they have focus rooms between them. And M-Branes is no such story. They sit inside the string theory, M theory structure, but you want to decouple them from all of that. You want to say, well, I don't worry about gravity in 11 dimensions. I just want to know what's the interactions of these branes when they're nearby.
Again, one point is just like if you want a single M2 brane M theory, you take a single D2 brane.
Yeah, the beginning of the sentence sounds like it's single M2, and then it ends up talking about n D2. So
oh, okay. All right. Yeah, that's indeed correct. So, what's screwing me up is I said the M2 brane SCFT, and by that I mean a family of superconformal field theories associated to a number of branes. Yes, sorry. Maybe I should have said SCFTs, perhaps.
Or SCFTs of n.
Yes, so there's not one SCFT, there's one for each n. Okay. Now the fact that you lift from 10 dimensions to 11 dimensions means that this is a 2 plus 1 dimensional object that was sitting in 10 with the D2 brane and now sitting in 11 dimensions, which means that the symmetries associated to the transverse space go from rotations in 7 dimensions to rotations in 8 dimensions. And so that's the geometrical statement. The corresponding statement of quantum field theory is that in strong coupling at the IR fixed point of 3D super Yang-Mills, the R symmetry is enhanced from SO7 to SO8. So, N theory, if you like, it predicts the existence of a 3D superconformal field theory with maximal supersymmetry and SO8 R symmetry. Now, there's a classification of such theories by Nahm long ago, and of course that's on the list to you. And Nahm classified this superconformal field theories that are allowed by the algebra. This is saying, well, indeed there is such a theory. It's a slightly different statement that there are dynamics there, as opposed to there is superconformal group. Yeah.
What does your L mean as a sociotechnics?
Yeah, so it's not left and right, excuse me. L means Lorentz, and R means R symmetry. So Yeah, that's the SO1, 2 is just the Lorentz group of 3 dimensions. So the thinking on the slide is that this is ultimately a statement about gauge theory, quantum field theory that arises from M theory. What I was saying earlier. I've muttered the words 10 and 11 and strings and branes and gravity, but actually this statement is just a statement about quantum field theory. And it is, in some sense, a prediction. It's not a prediction that you're going to test at the LHC, but it's a prediction about the nature of quantum field theory, which you can go and verify. So indeed, the relevant theories can now be constructed. So the first one is the one I'm associated with, which is BLG, which has got manifest, and manifest is important here, maximal supersymmetry. So it's got everything you wanted on that list. It's got 16 supersymmetries, maximal supersymmetry. It has SO8R symmetry and SO1,2 Lorentz symmetry. It's based on the gauge group. It's a gauge theory. The gauge group, well, there's actually 2 choices. We'll get back to that. It's SU2 times SU symmetry. But it's rather limited because it only describes 2 or 3, we'll come back to that, M2’s in some orbital form. So it's not the general answer. But it was, in some sense, easiest to find. And then came the development of ABJM, who just told us how to do an arbitrary number of M2’s. And you have to sort of make some sacrifices to do that, and you give up manifest manifest supersymmetry, and you only have 3/4 of 3/4 of 16, which is 12. And there's a variant of that called ABJ. Their gauge groups are UM times UN for any M and it describes N, where N is the smaller of the 2, branes. So that's the sort of the answer, if you like. The story goes on. So let me now reverse the timeline. So that's the recent development. Quite some time ago, Cao and Lee showed that if you were looking at 3-dimensional Chern-Simons theories, you can always have N equals 2 supersymmetry. That's rather trivial because you just got the matter and the Chern-Simons and they don't talk to each other at N equals 2. You can promote it to N equals 3 if you choose the gauge coupling constant to be related to the Chern-Simons level. That enhances things to N equals 3, and that was the observation of Bosons. And it was thought that was the maximum. But then the N equals 8 theory came, and then the N equals 6, and now there's a zoology between N equals 4 to 8. And they're all Chern-Simons matter theories. And what I think will be of interest to this audience is that the way to think about these theories, in my mind, is through 3 algebras. That's the structure that's encoding the relationship between the amount of supersymmetry and the gauge group. So, one of the real novelties, what's new in some sense, and I'll mention this later no doubt. What's novel about these theories, which does not normally happen in supersymmetric field theory, is that the amount of supersymmetry is determined by the gauge group. So normally, if you teach supersymmetry course and you just do Yang-Mills theory, and you throw in matter and whatever, the supersymmetry is oblivious to the gauge group. It doesn't matter what gauge group you use. But here, it's the opposite. The gauge group is telling you. So this list is actually a list of gauge groups. And the gauge groups are rather peculiar from a point of view. They're not SUN, or single SUNs. They're always product groups. Okay. So from a mathematical point of view, and here I do apologize because I am not a fully fledged mathematician, so I might be a little vague. But what do I mean by 3 algebra? So in the most general sense, it's simply a vector space, V, which has a triple product that maps back to the vector space. And then I've used a big word here, endomorphism. But the idea is you have an analog of the adjoint map. If you think about a Lie algebra, you have the adjoint map. And the crucial thing about Lie algebras is that the adjoint map is itself a representation of the Lie algebra on itself. So here you do a similar thing, means you have to fill up 2 slots with elements of your vector space, and that gives you a map from V to V. And you want that to be a derivation, meaning it satisfies this property. And this gives you the so-called fundamental identity. Since we're doing physics, we need to have an inner product, gauge invariant inner product on V. Well, what do I mean by that? Well, so you've got typically you want a positive definite inner product, so that V plus V to R. And then it induces an invariant inner product on the space of derivations, on the space of these endomorphisms. So the brown brackets are an inner product on the space of maps from B to V, and the angled brackets an inner product on V. T here is a generic derivation, and phi is this very specific derivation generated that way. You can also imagine a complex version, or Hermitian version of this, where the vector space has a homomorphic structure, complex structure, and so you can imagine a V bar, and then you've got a triple product where one entry is from V bar, and one entry is the other two are from V, and that maps V to V, and there would be a similar one from V bar plus V bar plus V to V bar. Similar story, you want an inner product, positive definite, V to V, this time we're going to C, and the analog of the adjoint map is very similar. You soak up the second two indices, one is in V, one is in V bar, and that gives you a map from V to V, and it's a conjugated version of it, and you want that to be a derivation. So that's all one, in my mind, all you mean by a three algebra. But the key point of this, what's called the fundamental identity, this notion that the action of this phi is a derivation, is it tells you that actually, if you look at the set of all such derivations, that's a Lie algebra acting on V. So the space of all, go back to here. So the space of all phi's of this form, which map from V to V, forms a Lie algebra because of this on V. So mathematically, that's just saying that V is a representation of G. So if you take a three algebra, you naturally get a Lie algebra along with some preferred representation. And in fact, this is an equivalence due to Faulkner, I believe it dates back to. Given any Lie algebra and representation, and you need inner products, one can always construct a triple product which satisfies the fundamental identity. So it's just, this notion of a three algebra is a different way of encoding this information, which is simply V carries a representation of G. And there's various ones, but the ones of interest, certainly for the M2 models, are classified by these people here, who might be well known to you guys. Okay. So you don't have to use this language of three algebras, and frankly, most people, when they talk about M2 don't. But why do I think it's interesting? Why do I think it's useful? Why are we still talking about it? And why do I think you might find it interesting? Well, it's this three algebra structure that encodes this data about the representation and the gauge group, which tells you how much supersymmetry you have, which is the novelty of these theories. And in fact, why they were so hard to, well, they were that hard, they took so long to discover them, is because you just get very strange choices for what the gauge group is, in terms of what the field theory is. So the amount of supersymmetry is determined by the gauge algebra and matter representation. So that's the novelty. And this actually would appear to, well, I'll come back to it. Let me just go to the next slide. Actually, we can do this slide. I should have done some different order, perhaps. I'll tell you what, let me keep the order I had in mind. So we will return to this point after I've given some examples. Okay, so let's just give examples. So this BLG theory is where V is real, and this triple product is taken to be totally antisymmetric. So when I defined the three algebra, I never said what the symmetry properties of the triple product were. And that's the key, in some sense. So the simplest thing might be to take it to be totally antisymmetric, and that will give you a theory with n equals 8 supersymmetry. So don't worry too much about the symbols. This is a standard expression. This is really all you think of. Here, the fermions tell you everything in supersymmetric theories, pretty much. This is the fermion variation. So this is the free stuff. This is a free thing. Here you see the triple product showing up here, and this is just totally antisymmetric, so you need this to be totally antisymmetric. And you can construct a Lagrangian, and it's relatively simple, kinetic terms, a Yukawa-like term from the triple product, a potential, which is just the square of the triple product, and then a Chern-Simons term, which is also given by this triple product because it's given by this inner product that's inherited from the triple product. So that's the argument. But the point is that asking for something that's totally antisymmetric is very restricted, and there's basically only one example, as was proven by these arguments. And that's where you have a vector space which is R4, which generates TA, 1 to 4, and we'll return to this, and the triple product is just up to some coefficient, it's just epsilon ABCD. Well, it's quite easy to see that if you look at what the gauge algebra is, the space of derivations you get by filling up the last two and acting on the first one, well, it's just any rotations, anything in SO4. But SO4 splits into SU2 plus and FU2 minus, self-dual and anti-self-dual rotations. So it's SU2 plus SU2. And this gauge invariant inner product that you get on the Lie algebra is just K over 4 pi times the trace of the self-dual ones minus K over 4 pi times the trace of the negative of the anti-self-dual. So the Chern-Simons term is just the difference between these two brackets. And the fields are, well, they're just vectors of SO4, but if you think of them, they're really 2 plus 2. They're the bifundamental of SU2 plus SU2. So standard result in quantum field theory, that if you have a Chern-Simons term like that, K has to be integer. And so this is features up here. So there are no continuous parameters. To do ABJM, because that's it. It's this unique choice. It's totally antisymmetric. You could go to the next weakest level, if you like. And then we have a complex structure. So you take this, there are 8 scalar fields, xi, and you split them into 4 complex fields, za, which you can imagine how you do, and here's the notation, which I don't suggest you worry too much about. The supersymmetries is then split to capital A, capital B run from 1 to 4. And the 16 components that we had of that spinner, because it was a spinner in 11 dimensions, which was chiral in a certain sense, are reduced to this epsilon AB. So there's 6 of them, it turns out, in SU4. But this is just some notation.
Excuse me?
Yeah.
Can this action be interpreted as a kind of Euclidean version of three-dimensional gravity?
Which action?
The Chern-Simons is pretty much similar to 3D gravity.
Aha, I know what you're referring to. Well, my understanding of 3D gravity is the gauge group is SL2R.
Yes, that's why I'm saying Euclidean version.
Isn't the non-compactness critical for the gravity?
Yeah, it is non-compact for true gravity, but if you consider some Euclidization, then it will be pretty much of the same stuff.
Yeah, so in this, for this signature, it's actually, you can interpret it as a Euclidean gravity on Euclidean density, which is a sphere.
Yeah, that's easy. Sorry, this is ADS or DS gravity indeed. Yeah, that's what I have. Yeah.
I mean, there are, I guess the answer is yes, there's some relation.
Okay, thank you.
All right, so returning to the ABJM models, so you've got a complex triple product, and the action in this form, let's skip over it. So here's the n equals 6 supersymmetry. So the z's transform into the size, it's just more entities, but it's structurally the same, and then there's the triple product here, split up to the anyway. But the Lagrangian is basically the same. In fact, you'll see it is. So we've got scalar, kinetic terms, potential, and Chern-Simons terms, and the Yukawa terms. They're all just Yukawa terms. They're split up a little bit today. The potential is again the square of something that is triple product, again with some peculiar factors. But you just take, in some sense, you're just taking this theory which had SO8 symmetry, you're splitting it down, so now you've only got SU4, and you split it up into its various pieces. The Chern-Simons term keeps the same structure. But the key point is that now you have an infinite number of examples of triple products that satisfy all you need them to satisfy to get n equals 6 supersymmetry. And one class is you just consider the space of m by n complex matrices. And so you take the natural inner product, you get the trace of AB dagger. And then this is the triple product. So you don't have a product of n by n matrices, but you do have a triple product. A C dagger B minus B C dagger A. So it's easy to see that the group generated by this, so these derivations, are just simply that the variation of Z is some matrix times acting on the left, and minus the matrix acting on the right. And this matrix is this V dagger U, and N is U V dagger. So these are n by n and n by n matrices. So it turns out that the gauge invariant inner product is simply k over 4 pi trace, or minus k over 4 pi trace for the, so this is the n by n and the n by n. That all falls out of the formalism. So the gauge group is clearly um times with matter in the bi-fundamental. So this is the famous ABJM model. There's some special cases that fall out too. So if you take n equals n, actually you find SUN times SUN, and then you could put the U1 back by hand or not. So there's a sort of family of solutions here. And then the ABJ theories are when m is not equal to n. And of course, if you take m equals 2, then you recover this PLG, the maximum supersymmetric one. It's just written in a form for which all the symmetries are not manifest, but it is exactly the same theory. So the list now continues. What I've told you is how do you construct the maximal supersymmetric theory, and then there's these n equals 6 theories. There are actually other n equals 6 theories, and then there's n equals 5 and n equals 4. The actions basically are the same. Once you've written down this ABJM form for the action, oops, I'm running wrong way. Not much changes. What changes is what choice you have for the triple product. So the novelties, and I think there are two, and they sort of break the rules. Of course, they don't, since I'm talking to mathematicians, there are theorems, and these do not violate the theorems because they're theorems. The problem is the theorems are often misstated, and these just sneak in under the wire. So what's different? Well, the gauge fields and matter fields are in the same multiplet, but not in the same representation of the gauge group. So that's the first theorem you might learn about supersymmetry, is if things are related by supersymmetry, they sit in the same gauge group. Well, that's violated here, because everything's related to each other by supersymmetry, but the matter fields do not live in the same representation, they're not in the adjunct. And the second one, which, well, I don't know if any theorem for this, is that the amount of supersymmetry is determined by the gauge group, if you will, as I mentioned several times. Now, of course, this isn't a violation because it's short. The fine print of this theorem says you're looking at on-shell states, and on-shell, the gauge fields have no degrees of freedom, so they don't count. To my mind, the three-algebra formalism is quite useful because it's what showed up, this structure. It's where you most naturally see the relationship between the choice of the gauge group and the amount of supersymmetry. So there's sort of this diagram, you have the amount of manifest supersymmetry, I'll come back to this point, which depends on the gauge group and matter representation, which is encoded by this three-algebra symmetry structures. So there's this triangle, and the examples are basically that if you wanted a totally antisymmetric, so this is just the structure constants, a way of writing the three-algebra on the basis. So it's totally antisymmetric, you can really get n equals 8, but the gauge group is this. The next thing might be to have this sort of complex structure, where it's antisymmetric in the first two indices, and you can swap the first two and the last two by complex conjugation, sort of like the symmetry of the Riemann tensor, if you like. And that gives you the n equals 6. Turns out there's two choices. I gave you the un plus un. These are the algebras of the group. There's also SPN and u1. And this has a brain interpretation as well, in terms of brains are orbital. N equals 5, you relax this constraint a little bit. This isn't quite right, but I couldn't figure out a cute way to say it on the page. But then there are three choices: SPN plus SUM, SO7 plus SU2, and G2 plus SU2. So this is just a weird list, right? Who wanted that? But that's the way it is.
Why no n equals 7?
Sorry?
Why no 7? N equals 7.
Oh, n equals 7 implies n equals 8.
Does the global form of the gauge group matter? Or
Yes. Coming up on my slides. So that's why I've only put the algebra here. So every subtlety matters.
But n equals 6, it's still got n equals 8 supersymmetry, which is on manifest.
So I've used the word manifest.
Yeah.
Not always, not for generic K.
No, that's okay. So I was going to ask, so when you've got, for example, the n equals 5,
Yeah.
is it that it's not manifest, or is it just not there? I mean, I assume it's...
Yeah, I don't know the full answer to that question. So I'd be very careful to use the word manifest here, which I may not have said all the time. Okay. One of my next points will be that these theories, you construct it, you write them down, you think you're home free, but they're not, because there's lots of subtleties, and there can be additional symmetries which are not manifest. And they will arise for specific values of this k, typically. Certainly the case that everyone studies the most, namely ABJM, k equals 1 and k equals 2 are special, and then k equals 3 onwards more or less generic. Of course, and by the way, going to large K is going to weak coupling, as from a theoretical physics point of view. But mostly one's interested in K equals 1, 2. You might be interested in the weak coupling limits. If you're thinking about straightforward 11-dimensional M theory, one's largely interested in K equals 1 and K equals 2, which is strongly coupled. And then it turns out these theories can have additional symmetries, and which are not manifest in the Lagrangian. So that's one of the lessons that I want to impart today. Okay. So, are there any questions today?
So it's n equal 4, so fully captured by 3 algebra?
I believe so. I mean, 3 algebra is a very general concept if you start in this full notion. So it's really captured by these supergroups that guys are written. But you can phrase that in 3 algebra. Because it's so generic in 3 algebra. It's just, you give me a gauge, you give me a gauge group and you give me a representation. That's it.
For n equals 3 or less, how we can classify these transimals matrices into 2? Is that right? They were captured by 3 algebra and probably not.
Well, they're all captured by 3 algebra. That's what you mean. But because it's to be understood, it's a very general concept.
Or do you think all n equals 3 or less equal symmetric theory transimals matrices can be captured using some 3 algebra?
Yes, but it's probably not useful. Because if you give me a gauge theory, it's got a gauge group, and it's got matter and sitting around representation. That data is a 3 algebra data. So there is a 3 algebra that describes that. How useful a description it is, that might be very different. Because what happens is k equals 3 simply ties the Chern-Simons to the matter, the coupling constant. So that doesn't tell you anything about the representation. It's going above n equals 3 that you have to choose the gauge group. And that's where this 3 algebra language is useful, I think. Okay. So now we want to do some physical analysis of these theories. I mean, I've just told you there's series. These theories have, well, we have here these have n equals 8, n equals 6 for ABJM. Why do we think they have to do with branes and M theory? Okay. So I've got several slides here, and I'm going to rush through them because it's a calculation, and I just want to highlight certain parts of it. So bear with me and ask questions. So I'm going to do it in ABJM because this is a story of minus signs and factors of 2 pi. So I'll just do it for a concrete case and tell you that things can be different if you worry about different things. So let's do it for ABJM. So you have this triple product, the vacuum moduli space of the theory, that's the space of zero energy states, which in M theory it should be how you can place your branes in space-time. Okay, so turns out you need to set the triple product to 0, and that turns out that these sets are commuting. We'll just do the case ABJM so that both n by n matrices. So it turns out they commute. So you can diagonalize them because there's a gauge transformation you make a diagonal with some eigenvalues z1 to zn, little a. Actually, that should be capital A. So it's perhaps not obvious, but it's true. But of course, you need to identify fields that differ by gauge transformations, but the gauge transformations are larger than the case for D-branes. So this is a similar story for D-branes, where you have commuting matrices. But in D-branes, you have the adjoint action, and here you have the bifundamental action. Well, you can still set the left and right equal and choose things like that, which allows you to permute the various eigenvectors. Okay, so there's a Zn acting on them, like there is in D-brane. But the point that's different is, unlike D-branes, there's still a U1. There's U1 to the n left, because you can take G left not equal to G right here, but up to a phase, the U1 phase. So you get this little U1 phase that's acting on all the Zs, which you can imagine, for example, by taking these gauge transformations. a critical difference. Well, how do you deal with it? This is a bit lengthy. So you go down to the vacuum moduli space, you write everything in terms of these U1s, just the diagonal elements. So now you've got this Zi, this I go from 1 to capital N. This is what the Lagrangian looks like for Zi5. Everything's been broken down to the diagonal. Like I said, please don't worry too much about the details. But you have to do a bit of messing around with the gauge fields. So I'm just going to show you what to do. And here's the key line, is you want to dualize this field Q. Q is just simply, where is it? It's written here. So there, it's the sum of the left and right, and so you can sort of diagonalize them by taking the difference in the sum. E is the difference, and Q is the sum of the left and right gauge field. It's a long story, but you can dualize Q. It turns out that you can do that, even though there's fields that are coupling to a left and a right, but they only couple to this B gauge field, the difference, they don't couple to the sum, so you can dualize the sum. And you do that by introducing a Lagrange multiplier for its field strength. That's the field strength of Q. And then these sigma i's, the Lagrange multipliers, well, you can integrate out the fluxes, and you find that B is K inverse d mu sigma. So this is a dual photon, if you like. So these B's are the differences, and they get dual photonized, if you like. And then everything's pure gauge. Lagrangian just reduces to this, where these W's are some dressing of the Z's. So this is relatively simple to do. I've skipped through the slide because it's just a bunch of calculations, excuse me. But the key point is simply that we've gone to the moduli space, we've gone to the U1s, we've rearranged the gauge fields rather than A left, A right, we've got the difference in the sum, and then we've integrated out the sum. And you get this thing, and this tells you that, oh look, this is just 4 complex scalar fields. So C4 is the moduli space. Mod symmetric group, which we had earlier. Mod something else, because these sigmas are periodic. These are dual photons. And again, it's a calculation that tells you what their periodicity is. The periodicity is 2 pi because of Dirac quantization law. Okay. But why have I gone through this? This is I hesitated to. There's a lesson here, that's why. This is very sensitive to the global choice of the gauge group. So somebody asked about what the gauge group was. And in the action, it doesn't matter. But when it comes to the moduli space calculations, it's very sensitive to what the gauge groups are. Because it affects the fluxes, it affects the periodicities of the sigma. So sigma is periodicity 2 pi, and W is the stress factor, so actually the W's have a periodicity, not 4. So actually, it's not R8 or C4, it's C4 mod ZK. In the vacuum moduli space, it's the same part of that. That's what you expect for capital N M2’s on a C4 mod ZK transverse space. And indeed, what's happened here is indeed, you see for generic K, this is what breaks you down from maximal supersymmetry down to 3/4 supersymmetry, from 16 to 12, is the overall. Of course, special things happen at K equals 1 and K equals 2, because at K equals 1, there is no overfold. You would expect maximal supersymmetry. K equals 2, the overfold is half supersymmetric, but it's the same half supersymmetry of the M2’s. So again, you expect 16 supersymmetry. So the line of, so what I'm trying to capture here is you have this theory, you look at it, you dress it up. I'm going to come back to these calculations a little bit later. Okay, so why did I go through this rather lengthy discussion? Well, so here we have the ZA that I wrote down in terms of diagonal elements. Suppose now I want to describe not M2’s, but M2’s that are moving. So naively, you would say, well, let's just let them go. You know, so the U1 phase might be interesting. So let's let them just move, give them a little time-dependent phase. So you think you're picking your M2’s and making them move around the extra 11 dimensions, right? But you're not. Because that's a gauge transformation away. That's not a gauge invariant thing to say. You can't do that. Because you've got these extra gauge symmetries, which don't really exist in the D-brane analogy. So the question is, how do these, dynamically, how do the M2’s probe this extra 11 dimensions. So they take up 3 of the extra dimensions. They see 8 extra dimensions transversely. And the big thing is, how do they see all of that 8 dimensions? So one thing to do is to construct the Hamiltonian, which is just sort of some momenta, some derivatives, potential, yeah. But then you get the Gauss law terms. So this is telling you that the fluxes are related to these combinations of momenta, because you've got a Gauss law constraint. These must vanish. So in particular, the Gauss law constraint relates the fluxes to the left and right gauge field in terms of these combinations of z's and their momenta. So if we go back to our vacuum moduli space, so we're just parameterizing z's in terms of these eigenvalues, this constraint, the Gauss law constraint, becomes that the fluxes, well, they have to be equal, turns out. If you write it out this way, it's just d0 theta r. d0 theta, that should be theta 1. So in other words, the momentum around the circle is the flux. And this is a more formal way of just dualization. If I think about classic 3-dimensional dualization of a scalar field into a gauge field, vice versa, you have a relationship like that. So and then you see that the time derivative of this scalar field is F12, and so if you evaluate sort of the momentum and the inertia charge, it's just the flux. So the next question, so that's sort of the dynamics of these moving M2's. It's not as simple as just letting them become time dependent, but it's actually captured by these fluxes. That's the more gauge invariant statement. So in particular, if I return to this thing as an SCFT, then I'm looking at, I want to evaluate various expectation values of operators. But things are not as gauge invariant as they used to be, as you might be used to. So for example, here's a string of operators that makes sense. It's an Z, an anti-homomorphic Z, a Z. So this, remember, is an M by N matrix, but this is an N by M matrix, and so this all makes perfect sense. This does not. This is not a gauge invariant operator, if I should put a trace there. This is not meaningful in APJ theory. But this guy, you can see, has 0 U1 charge. It's +1 minus 1 plus 1 minus, etc. Here it's got charge, but it's not gauge invariant. So it's how do you see, and these charges are basically the momentum in the extra dimension. So how do you explore the, when it really comes down to it, you want to look at this thing as an object in M theory, how do you explore the 11th dimension? And the answer is you have to use monofold operators or atomic operators. They date back to 1976. The idea is you need an operator. So these are new types of operators from the point of view of classical field theory. Of course, they're not new because they're written down by atomic in 1976. They are what I mean by like a quantum operator. They are an operator that exists in quantum theory that is not constructed out of some polynomial of the fields that you construct in classical theory. They are defined by a prescription of the path integral. So putting a monopole operator into a correlation function says, okay, what do? I change the boundary conditions of the fields in the path integral, and then the rest is the local stuff that you've done before. This is a local operator. This part here is what you always do with path integral, some operator times the action. But rather than integrate over all fields, you integrate over a field that has specific singularity at the point y. So now you're in Euclidean space, because you're doing path integral. You pick a point y, you surround it by 2 spheres, and you demand that there's a flux in that 2 sphere, which means the fields are singular. There's a direct monopole singularity in the field. And that's specified by this Qm, which is some element of the gauge group. So satisfying direct quantization condition. So you're basically integrating over fields which have singularities. So this is a new class of operator. And it turns out that because of the Chern-Simons, these operators are not gauge invariant. It's a simple calculation. They shift. And there's a beautiful long story, it's quite long and detailed, that these operators sit in representations of the gauge group, which are determined by the charge. And in particular, the representation has the highest weight lambda, which is k times the magnetic charge that you put into the singularity. So it's a little long story, it's a little complicated, so I'm rushing it. But get the picture that there are these important non-perturbative non-Lagrangian operators. There's a slightly easier way to see it if we go back to the moduli space. Remember I wrote down this horrible action, which is just what you get by assuming the fields are all diagonal. So the monopole operators are just EPI sigma. And you can see that, because if I put EPI sigma in expectation value, well, here's my path integral, here's EPI sigma, here's my operator, here's my action. Well, this is EPI sigma. I can replace that, I can move it into the action by replacing it with the delta function. And if I look back at the action here, you see that all you're doing is you're changing DH plus a delta function source. So it's telling you that you're inserting a magnetic flux into this H, which is the sum of two H's. So these are the monopole operators in the U1 theory, the helium theory. They're just e to the I sigma. But the point of this definition here is this extends to the full theory, the non-abelian theory, where you can't dualize the photons.
Sorry, what was sigma?
So sigma, yeah. This was the point where you were probably wondering at this point, why is he going through this? And that was why. So what we did, way back, we did the moduli space calculation, was we wrote everything out diagonally, and then we dualized Q, which is the, where is it? Q is the sum of the two gauge fields. So you do two things. You had a left and a right gauge field. You now split them into a difference and a sum. The sum is called Q. And then you dualize Q. Okay? And so sigma I unduals to Q. And they're popping up here because they're simply the monopole operator. And that's how we got to here. And then if I look at my moduli space, remember I had this parameter in here, well that's just this monopole operator to 1 over k power in this notation. But indeed, these monopoles have charge k, so it makes sense. So this dressing that we did, it looked kind of simple at the level of the moduli space, is actually a rather non-trivial statement about introducing non-trivial operators into the theory. So, to sum it up in a way, yes, I wrote down this Lagrangian, ABJM theory and BLG is the same for this. It's supposed to describe physics in 11 dimensions. Okay, zero dollar question. You told me you've got a physics that describes M2 branes in 11 dimensions. How do I even translate, move an M2 brane in extra dimensions, in the transverse space? So normally you have a translation operator in the gauge theory, which is just d mu z or d mu x. That's the conserved current associated to translations of a brane. But that's not really invariant in this theory. You can't do it. You have to dress it up with a monopole operator. You know, in the moduli space, it means doing this. But in the full theory, it means introducing a monopole operator. This is the translation operator. It's not like Yang-Mills theory. Yang-Mills theory, you want to take, translate the branes off direction. You just take everything and you shift it by the center of mass motion, degree of freedom. The center of mass degree of freedom is just the diagonal you want. Just you shift all the matrices by their density. You don't do that in these models. So, yes, there are 11-dimensional models, but the 11-dimensional physics is actually quite obscured from point of view. You have to introduce these non-trivial operators just to describe how you move an M2 brane from here to there. Yeah. And the supersymmetries are similar. So for k equals 1 and 2, you get more supersymmetry. Well, you have to dress up by this operator, not gauge invariant. You have to include a monopole operator with 2 lambda 1 the highest weight. And it turns out this still only works for k equals 1 and 2. So some basic physics of 11 dimensions is actually gone from the classical model. That's the lesson I want you to draw from this. Everybody thinks ABJM is simple, BLG is simple, but it's not. So the most basic 11-dimensional physics is obscured completely. Because you can't translate branes in the transfer space.
Yeah. So, if I was to do a D-brane analogy, then if I do SU2 D-branes, for example, I wouldn't capture the translation mode so much because I've factored out the U1.
Yes.
So really, the SU2 is only, if you like, the relative degrees of freedom between the
Yes.
two layers. So is there not really secretly in ABJM also U1 have to be factored out, which is the centre of mass?
No, it's there. It's in the monopole operator.
So it's the one.
So there are very sophisticated calculations done by people in superconformal indices and various things like Kapustin and Dashkirov and some work by Kufu and Brennan and some others, where they can literally show you that there is a U1, free U1 multiplet in ABJM. So the Lagrangians are perfect SR, right? There's not fault with the Lagrangians, the actions. They are good. But to see the fact the U1 in the center of mass motion is not triggered. It doesn't arise by a classical field. It arises as a quantum field.
Yeah, actually there would be decoupling also, we can factor that out at young units, but you're saying that this decoupling is happening on top of it.
Yes. So what happens, this is the guy. This is the translation of, well, these are the monopole operators. And they only exist at k equals 1 and 2. For reasons that I've brushed over, but well, it has to do with the fact that you need the monopole operator to have this this monopole operator, which sits in the fundamental. The problem is that the monopole operators, because the Chern-Simons term, pick up a charge k times the Chern flux. So if you want this to be, and this flux has to be a fundamental weight. That's this GNO construction. So this has to be a fundamental weight. You want this to be lambda 1. So you have the k times the fundamental weight is lambda 1. The only solution is k equals 1. You can only do it at k equals 1. This operator only exists at k equals 1. And at k equals 1, it decouples. Of course, there's a multiplet of them, and they decouple from the rest of the theory. You can see that in typical momentum. So it's all there. This is really the lesson that I want to impart from M2’s. You thought that you'd home free because you had Lagrangian and you could do what you like. But the Lagrangian is very sophisticated, and it's hiding things and putting them somewhere else. They're in the non-perturbative. You have to think of these theories in the full non-perturbative way. You can't just look at the classical limit, because that's describing k equals infinity, which is actually very, very different from just flat space, which is M theory.
Is it easy to see what happens to the monopole operators when you reduce to the M2’s if you do this coupling expansion?
So they certainly still exist in the D2 brane, because you can introduce them into. Sure. When it's hoped to introduce monopole operators, it's definitely thinking about.
Of course, but if I just translate right in the D2 brane picture, there's no problem. Right? So
Yeah, so you can ask what's been achieved, really, if you want to be negative.
no, I mean, well, what happens to these things, right? I mean,
Yeah, they exist. So monopole operators are much easier to understand in superconformal field theories, because you can use state operator mappings. And then the monopole operator just becomes creation of a state with magnetic flux. And it's a little easier to handle. When you're off the conformal fixed point, you can't do that, and you really got to go back to that definition I gave you. And that's really tricky. But yes, they exist in those theories too. And they are what's happening. I mean, what's the other story? The D2 brane description of an M2 brane is as follows. I have three-dimensional superioritarials. It has monopole operators. These are basically just non-abelian ways of dualizing the photon. And in the IR, you get an enhanced symmetry. It's all there. The M2 brane does not have more information than the superioritarial, because it's just the IR limit of superioritarial. So you can certainly get to it from superioritarial, right?
I just meant in a naive picture by translation, right? In the D2 brane picture, just shift by scalars and so on. So that's
Yeah.
okay.
So what you need to do, so you've got 7 scalars. So what happens for D2 branes is you've got 7 scalars. And you can shift them as much as you like, because there's a center of mass motion, which is the identity matrix in UN. But what you're really after is how to move the D2 branes around the M theory circle. Yeah?
It's only for the
That's what going to M theory means. Otherwise, you're just a string theory. So you want to figure out how you're going to kick the D2 branes around the M theory circle. And the answer, one answer is, well, you dualize the photon, and then you classify the energy. You can't do that because it's not a really engaged theory. But you can basically do it with monopole operators. It's all there in the D2 brane theory, just packaged differently.
So actually, if that's then momentum in the M-theory circle, are they not MD0 branes?
Yes. So the 0 branes dissolved onto D2 branes is flux. It's all the same. Okay. Here's a slide, by the way, out of curiosity, because I still think, how does BLG go away? Because BLG had more of what you want, it had more manifest symbols, although it still has this problem that if you want to describe translating the brains, you need multiple operators. So there's a list here which is probably incomprehensible about how it maps to ABJM, and it's rather cute in some sense. So basically, they agree for 2 M2 brains, and there's a paper last November showed that actually the BLG describes the interacting part of 3 M2s, which is a novelty. I particularly like this last paper because actually the second paper, or the paper we wrote on, we claimed this actually. We had no idea what we were doing. So we claimed this without knowing any of the complications that I showed you. And I always thought I was being a complete idiot. It was a very, just a random claim, but it turns out to be true. But I credit this proof for it. Okay. So, okay, we're through the first 15 minutes of my talk, so let me summarize. So what have I tried to explain about M2 branes? It's too much to, maybe it's too much to ask for all symmetries to be manifest, but easy to get to. Yeah? Nobody told you that the symmetries and structures are just there for easy pickings. They've got to be there, but they might be obscure. Another little lesson which feeds into my last hour, after the next hour, is for 2 M2 branes, more symmetries are manifest. It's restricted, you can only describe 2, but it does allow you to do more symmetries, and that might help you search. The next one is the quantum theory, which is what you're after. Right? You are after the quantum theory. The classical theory is typically some weird overfold limit in this case, but we're moving on to M5 branes. I don't even know what the classical M5 brane theory is. That doesn't really exist. So we're not interested in the classical M5 brane. And the quantum theory might be very, very different from the classical intuition. And in particular, you have to consider quantum operators like monopole operators to see the full physics. Other things which are more hope is that the role of the gauge group is non-trivial. Right? So for M2 branes, we saw that that determined the supersymmetry. And actually, it turns out that the global choice of the gauge group matters. So, for example, for BLG, so for ABJM, it's UN times UN, full story, end of story. But you can imagine UN times UN is U1, U1, SUN, SUN. You could put different Schoen-Simons levels, for example, in the U1s from the others. If you like. You don't, but you could. For BLG, for example, whether you take this gauge group or that gauge group, well, it affects the fluxes in the calculation, and it changes the space-time interpretation. Here, you get 2 M2 branes in RA, and here you get 2 M2 branes in RA on G. It depends on the global choice of gauge group. So these are substances. And the last question, which I would like to know, for generic K, there apparently is no M-theory interpretation of BLG, yet it has all the symmetries one expects. Well, not all the symmetries. As I said, it doesn't have these translations. But it's got a lot. It's got 16 supersymmetries in SO8R symmetry. But apparently it doesn't sit in M-theory. In fact, what you can show is in some cases, if you mod out BLG, you get ABJM. So it's higher than M-theory, if you like. You have to do something to it to get the M-theory result. You have to overfold it to get the M-theory result. So it suggests that there's maybe more to M-theory. There's perhaps a non-geometric phase of M-theory, which you have to do. Since I took my mandate at this conference to be totally speculative. Right? So that's speculation. All right. So I'm seriously running out of time. When should I finish? Like not 2 hours. 10:14? I'll try to. Yeah. So let me just move on to the M5s and the same 2 comes in. All right. So we start again. We're back in M-theory. Now we're looking at M5 branes. Their decoupling limit gives you an interacting SCFT in 5+1 dimensions. In one case, a single M5 brane, even that took some time to understand, and it was written, the equations were, there's an action here, another action here, equation of motion here. Right. Bottom line is it's a 6-dimensional object in 11 dimensions, so it has 5 scalar fields describing its fluctuations. The novelty is this 2 form. It doesn't have a 1 form, but a 2 form, with a self-dual field strength, H, M2’s. Linearized level, you just get free equation motion for x, free graph equation for psi, and H is self-dual and closed. It's related to speed. For n equals 1, you have this so-called AN 2.0 theory. So this is some strongly interacting theory in 6 dimensions. Some intuition about it. Well, you think of M5's like this, and it's thought that the dynamics comes from M2's which end upon it. And there's 2 types of M2's you can imagine. This one on the right is M2's coming in from infinity. They're sort of abelian M2's. They end on only one M5 brane. And you understood those long ago as simple solutions to those equations of motion on the other side, and the full nonlinear ones, where you get roughly a form like this. But these guys are the more interesting ones. This is self-dual string solitons, which are highly non-abelian. They live on in this case I've written the A1 theory, SU2 M5 branes. And I believe this is of great interest. I know Christian's done a lot of work being interested in trying to construct these solutions, because the analog in D-branes is the norm construction. So this is some M variation of the norm transform. Presumably that's interesting mathematics. So this theory is meant to be a theory of these self-dual strings. Those are the natural DPS objects. So this theory sort of sits on the edge between field theory and string theory, because it's not really got, it's not got BPS particle excitation, it's got BPS string excitation. And ADS-CFT tells us that its scaling goes like n cubed. So the number of degrees of freedom, whatever that might mean, goes like n cubed. So I say whatever that might mean is because you're in a strongly coupled situation where you don't necessarily have Lagrangian, so you mean the free energy. Okay. So let's do some basics. You can wrap it on a circle. So the dictionary tells us that that gives you ND4 branes in 2A string theory, and there's a coupling constant G string, which is R5 over L string. 5 is the radius of this fifth direction. Well, D4 branes are described by UN superdiagonals with coupling 4 pi squared times this. So one way to think about that is to say this 2,0 theory is the UV strong coupling completion of 5-dimensional superdiagonals. And then, from that way of thinking about it, what's enhancing is the Lorentz group, not the R symmetry. So you have a 5-dimensional field theory with an SO5R symmetry and a strong coupling, which is the UV. It flows, except that since you're going to the UV, you're underflowing to this. It enhances to a Lorentz symmetry. So again, this is another prediction of M theory. And it's a very, very striking prediction of M theory. Because to date, you can go ask your quantum field theory friends in any department you like, and you ask them to tell you how to construct a field theory above 4 dimensions, and they will not know how. A quantum field theory above 4 dimensions that's UV complete is a complete mystery to anybody, as far as I'm aware. And there's a lot of people who study quantum field theory. But it predicts that it exists. So I think it's actually very important to do this, because if we can learn how to do this, there's other people in other communities that would be very interested. Well, they might not care, but they would be forced to admit that they're learning something new in a subject that they consider fundamental. This field theory does know about this extra dimension, because we pointed out long ago by Rosales, who's the first person, that there are natural solitons in this theory, where you time-independent solutions which correspond to self-dual gauge theories hit self-dual gauge fields on the spatial components. So it's time-independent, and the spatial sections of the field strength just look like instantons. Anyway, so turns out that they have momentum which looks like n over R5, where n is the instanton number. And they are associated to a topological current F wedge. Reduction on T2. So let's reduce again, another circle, with radius R4. And here you find UN superdiagonals. Now we're looking at 4-dimensional superdiagonals. with coupling G squared, which is the ratio now. Because this is a fundamental point. We started off with it being proportional to R5, and when you reduce, it's 1 over G squared sits out in front of the action, so when you reduce, you pick up the factor of 2 pi R4. So that gives you this. So there's an S-duality, monotone and Olive S-duality, which swaps perturbative modes with monopoles, inverts the coupling, so it's swapping R4 with R5. Well, this is just swapping the two circles of the torus. It's a diffeomorphism. It's a modular transformation of T2. So one of the great claims of the 2,0 theory is it's manifestly embedding this monotone and Olive S-duality into itself, because it has diffeomorphisms, presumably, and those diffeomorphisms of T2 give you this S-duality. Well, that's got an immediate consequence, which is that, of course, a 4-dimensional superioring model is only self-dual for ADE gauge groups. So this 2,0 theory can only exist for ADE gauge groups. Otherwise, you reduce it on 2 torus and you get something self-dual, but it's got to be self. The only options are ADE. And in fact, it was first constructed by Witten, I think, to be string theory on K3 with an ADE in there. So we only think it exists for ADE. All right, so now I want to make important points, because there's been much discussion about this. We do not think that there is a Lagrangian description for M5’s. I know people claim that there was not a Lagrangian description for M2’s, although you can no longer find such people. They won't admit to it, because there was never really a good argument. But there are good arguments here, and they're worth paying attention to. I'm not saying there aren't ways around the arguments, but it's really important, I think, to keep these in mind. So the first thing is the following statement. What could it possibly be? If you're in 6th dimension and you want a renormalizable, well-defined vacuum. So here's 6th dimension. So you might start writing down the 3 form, HH, so it's self-dual, so this vanishes. Let's not even worry about that. What is the space of possible field theories that this is sitting in? Hard. So then you've got the scalar fields. Okay, that's fine. Free theory. What do you add next? So quantum field theory, you want to look for things that have dimensionless coupling constants. So the next order would be things like this. You could imagine something cubic in X, so potential is cubic in X, by cube theory. You might have gauge fields, so you might have an F squared. That's got dimension 4, X is dimension 2, so you can have something linear in X times X squared. Okay. You could do that, and as effective field theory, you can certainly write those down. But fundamentally, they're unbounded, so you can't define the theory this way, at least not without great care. But then you're stuck, because everything else you add is going to be non-normalizable. So, what is the space you're playing in? You come across this. Now, I'm not saying these problems aren't unsurmountable, but you have to keep this in mind. Perhaps there is something you can write down, and at certain points, you're going to be able to claim it's actually well defined. But that's very different from the usual mantra of quantum field theory, where things are generically fairly well defined and special things happen, in the IR, say. It might become super conformal. Usually you have to start with a good theory in the UV and flow down. And here there's no obvious candidate for a good theory. It is the UV theory. Next one's a cute little argument due to Witten, which is, I've already shown you that when you reduce to 4 dimensions, you get an action which goes like the ratio R4 over R5 times the action for a super Yang metal. But how do you get that from reduction of a 6-dimensional action? Because if you do that, then you expect something that's proportional to R5, not inversely proportional to R5. This is actually a super important point for the M5 frame, that when you reduce it on a small circle, you get weakly coupled theory. Normally, when you compactify a circle, you get a strongly coupled theory, a small radius.
Can there be some duality transformation from 60 to get to the final value?
Well, I'm not saying this is a killer argument. I'm just saying it's a non-trivial thing to do. And your theory must have it somehow. Perhaps you set some bev, you set some bev, and it just does that. So my question is, so your theory would be like, okay, you set a bev. Why do you choose that then? Okay. But again, you could go back, well, because that's the magic value for which an enhancement takes place, you know. So these things might work, but it's just things to keep in mind. The next argument is more killer, to my mind. It dates back to Whitten again. So let's reduce the theory on a manifold which has got B2 plus B2 plus and B2 minus, or all manifolds have B2 plus, B2 minus. But it leads to B2 plus chiral bosons and B2 minus anti-chiral bosons from the self-dual. So the previous statement had nothing to do with self-duality. Here we're saying self-dual fields are a problem. So you get a chiral theory with B2 plus chiral bosons and B2 minus anti-chiral bosons. But it's a well-known fact in 2 dimensions that there's no marginal invariant partition function unless the difference between the chiral and anti-chiral is 4. It's multiple of 8. But if you had a Lagrangian in 6 dimensions, and therefore a diffeomorphic invariant 6-dimensional theory, you'd get a marginal invariant action no matter what you did. Okay? So how do you reconcile this? Because there's certainly cases where there are not multiple of 8 chiral bosons. In fact, in some sense, that's the whole point of 2,0 theory, is it encodes manifest S duality, it encodes marginal invariance. And yes, for maximals for Yang mills in 4 dimensions, marginal invariance is S duality. Great. In 2 dimensions, marginal invariance is basically boils down to chirality, and no, it's not. There are a lot of chirals out there.
I mean, you've not coupled this to gravity. So I mean, I understand the argument, but all that argument says is that you couldn't have the field theory on its own. You need to have a field theory that will cancel some anomaly type term that will come from.
No, I mean, how do you
say that term can't exist?
I mean, how do you couple? You write down the Lagrangian. It's an action.
Sure.
So this action cannot have marginal invariance associated to it.
On its own, but you can then. I mean,
but action always does.
An example would be actually the string itself. The string action itself, and the T-duality, is anomalous in the sense that you'll get a certain number you'll get the partition function will shift depending on 0 nodes of certain of B1. But then you couple the dilaton and shift the dilaton at the same time when you couple to the order characteristic of the world sheet. And then that cancels that term. So all it says is if you take the field theory on its own with no coupling to gravity, then indeed you face this problem. But then the challenge is, if you do, to make it work, you need to include also a term that will cancel the anomalies through some extra complex.
I hear what you're saying, I think it's very interesting, and certainly one hopes that there's a way out of this.
I mean, what Whitten himself,
but I think it's the opposite of what you say. Namely, I would have to write down the Lagrangian, which depends on the manifold.
Yes, indeed, that's what's said by gravitational coupling. Because it puts the data of the manifold coupling into the theory.
Yeah. So it's not.
So that's what you do with D3.
The D3.
Yeah, which is N equals 4, right? So there you've got couplings which are basically between the order characteristic and the Hertzsprung signature of the D3 through R wedge R and R wedge star R, which you've got, which then couple to in the Westinghouse-Whitten terms of the D3, which cancel this sort of anomaly when you do S duality.
Here the problem is that there's no anomaly.
That's an anomaly in the sense that when you take modular invariant, you're taking a symmetry and then you're saying that the partition function shifts.
Yeah.
And then, so that happens exactly in the D3 when you do S duality.
I do what you're saying.
And then you cancel those terms with the introduction. In fact, they happen in string theory. The terms that you add, which are gravitational couplings, actually cancel the S duality anomaly, which is the modular transformation.
I see what you're saying. Okay. So
it's an important point.
We're saying
it's not that there's a definite no-go there. It says that you need
none of
to
these are absolute definite no-goes.
Yeah.
But given so much.
But it's exactly what we've seen already with M-Branes, that when we look at the partition function, we need to take data from the manifold, and so then we've got to couple topologically to the manifold to cancel this sort of term.
Yeah.
So to say it differently, you expect the 2,0 theory to have actually a gravitational anomaly in the diffeomorphism. But it's indeed it's a very precise one.
Yeah, in fact, the paper studies it. Yeah. Yes, that's another way of saying it. I mean, yeah. Okay, so let me continue because Then finally, there's this point. So I said it only exists for HE gauge groups. But it turns out that you can reduce it on S1 with sort of twisted boundary conditions, and then you can get the B and C gauge groups. Fine. But then at some talk, Tashikawa came up with this test. So if you have your 2,0 Lagrangian, and then you compactify it, adding a Z to a twist, and you do it for the SU2n, you need to get SO2n plus 1 out. So that's a little test. And obviously, the key point being, of course, that this is SO2n plus 1, not SO2n. It doesn't sit inside SUN. Otherwise, you could imagine some Higgsing. But yeah, so does your action do this? So these are challenges to be overcome if you want to have a Lagrangian formulation. All right. So let me talk about what people have done. So the first construction, I believe, was Aharon, Bakutz, Kashmir, Silverstein, and Seibler. And they did a DLCQ back in the day that was popular. So they consider null compactification. What do you mean by that? You have like-cone coordinates x0 and x5, xi, 1, 2, 3, 4, and you identify x minus with x minus plus 2 pi r minus. And you fix the momentum on this null circle. What do you mean by null circle? Well, what they mean by null circle is you start with a space-like circle x5, and you boost it, and you take the limit of infinite boost. So you write your boost as 1 minus epsilon squared, so it's going to 1, and this is identified as, say, 2 pi r5, so this you think you know what you're doing, but then it turns out that the null boost is r5 over epsilon. So here's key point number 1, is obviously to keep R5 compact, finite, sorry, you must shrink R5 to 0 in this limit. So R5 is going to 0 and epsilon is going to 0. But shrinking R5 to 0 means that you've got the M5 on the circle, which is shrinking to 0, so that's well described by 5D super mills. This is not trivial. If I did this for any other field theory, I would not be able to make this claim. Because normally, if you take a field theory and you compactify it, you go strongly coupled. And this is you're taking a field theory and you're compactifying it's going to weakly coupled. It relates back to that point, Witten's first objection that I gave. That the action is, comes out like 1 over R5, not R5. In this limit, we know what's happening. The instanton number is playing the role of the momentum, so K is traced F which F. So we're looking at the sector of 5D Studio Mills with instanton number K, and the dynamics just reduces to quantum mechanics from the moduli space of SU and instantons with instanton number K. So that's their proposal. So this relies heavily on this fact that the coupling constant squared goes like R5, not 1 over R5. It's a critical fact of this construction. Otherwise, it would not be useful at all to say you were a strongly coupled aspect of some other gauge theory. Okay. Oops. No, oops. The next one that came up is so-called deconstruction of these authors, which is curious because at the time, Karch and Montel were string theorists, and these three were phenomenologists. So what were they doing? Well, they were intrigued, because as I said, it's a quantum field theory question, and they're interested in quantum field theory. So you construct a quiver, what they call the Moose diagram. Well, if it's a Moose diagram, it's a bunch of SUKs, in a circle, and then bi-fundamental matter between them. From the brane diagram, it's like this. You have NS5 branes this way and D4 branes this way. So what happens is that each of these horizontals gives you SUK gauge theory, and then there's open strings between them. The NS5s do nothing except impose boundary regions in the bi-fundamental. So this is identified, it's a circle, so this side is identified with that side. So this gives a 4D n equals to superconformal field theory, because each SUK factor has NF equals 2K, 1K from the left and 1K from the right, from the right to the left. So this is the superconformal field theory. I missed something. You go out on the Higgs branch, so that you break the SUK to the n to SUK. And you have to carefully tune parameters so that you can take a limit where the number of nodes goes to infinity. And the coupling constant has to go to infinity, and the left gets tuned in a certain way. The periodicity, so you get a bunch of KK-like states come from strings that stretch around, like 1 brane, 2 branes, 3 branes, 4 branes. But for very large nodes, that looks like a KK tower up to a certain stage, and then it turns back on itself. So if you take a large limit, you get something like a KK tower below an energy scale. But because you have S-duality in this gauge theory, the KK tower is enhanced non-perturbatively, one-to-one duality, to an SL2 multiplier of 2 towers. And so actually you reconstruct, or deconstruct, I guess, a 6D theory with SO5 transfer. That's the 2,0. So, and this is actually, I think, they lay dormant for quite some time, but recently it's been used to make exact localization calculations. And it's, in my mind, in one level, it's actually quite a nice construction. Because, well, DLCQ, firstly, I have no intuition for how DLCQ works, but that's my point. Secondly, this does have problems because the instanton moduli space has singularities and you have to know how to deal with it. As far as I can tell, this construction is kosher. Like this, it's a limit of something and that something's well defined. Yeah. So that's good. How you take the limit, how you compute, well that's your problem. But it's at least it's the limit of something that's well defined, unambiguous. So we are our own one, this is my talk, I'll mention it, which is that maybe 5D superdiagonals is actually well defined non-perturbatively by itself. And is exact description of the 2,0 on the circle. So in other words, it's got this complete KK tower of soliton states. So our thinking was pretty naive. Well, it's already got the KK tower. Why would you take that away and replace it with something else? Now, of course, there's a big reason why I bother, and that's that it's naively non-normalizable. It's a 5-dimensional field theory. It's not normalizable. What we would like to argue is that it's not normalizable, but actually, if one knew how to compute it exactly in path integral somehow, you would find that non-perturbative physics would remove the divergences and make it all well behaved. And that comes about because you need these instantons to be small, zero size to at least of the size G squared. And in this story, again, it's going back to this idea I tried to impose earlier, is that you really need to think of the theory quantum mechanically, non-perturbatively. And then you have an analog of monopole operators called instanton operators, where now you're in 5 dimensions, and the instruction is for an instanton operator is that you take an insertion point, so remember you're in a Euclidean 5-dimensional space, you can surround a point by a force field, and on that force field you can demand there's an instanton number. So that's an operator in this theory, and we like to think that that's inserting extra dimensional momentum. And certainly there have been some successes. This thing that you might say, where the hell, for example, is n cubed, if I'm just talking about a UA gauge theory in 5 dimensions, but it has been seen in some pretty sophisticated localization calculations. So a comment. The claim here would be that 5D superdiagonals does provide an action for 2,0 theory, but it's a 2,0 theory in a specific manifold, one which is of the form S1 times something else. Now, of course, if it's S1 times something else, and as I meant to say that there's also an R11 here, then V2 plus is V2 minus, and this chiral mode problem goes away. But you might ask, what if I took a M4's multi-tau nut? So its multi-tau nut has a V2 plus. So therefore it has chiral modes. And the way to see that is that if you reduce to 2A, you get D4 branes, but the zeros of this S1 vibration give you D6 branes. D6 branes intersecting with D4 branes, you get the so-called Dn equals H strings, give you chiral charged modes. You can put 5D superdiagonals on a circle, on the circle vibration, and it was done by these authors, basically. You get a variation of the Chen-Simonson, and the chiral modes then exist as solitons. So we did something a few months ago, but mentioned briefly by Olsen a few years ago. So in this case, you see that things are kind of working nicely for you. You do get chiral modes, but they come out to non-perturbative physics. Okay. And I just mentioned that actually these three descriptions in my mind are all deeply related. And which one you like, which one you hate, that's up to you. My key point about the GLCQ description is it's apparently giving you a description of the 2,0 theory. And the 2,0 theory is the UV completion of 5D superangles. Yet the only information that went into the GLCQ description was the information of 5D superangles in the IR. There's no new degrees of freedom have been added. Although there's an issue about how you deal with the singularities in light. And the action that you get from deconstruction is like a lattice-like regularization of 5D superangles. Another way to say this, and this might be seen an obscure statement there, but there was one. What do you mean by 5D superangles? It's naively a non-normalizable theory. It only exists, in some sense, as the 2,0 theory on a circle. They're synonymous. Language is simply about what you mean by 5D superangles. Okay. I also, I'm running out of time, other proposals in the literature. Some people in this room have got their theories, and I don't mean to be dismissive of them. I've already run out of time. And frankly, they should talk to you about their work, not me. So there's twisters-inspired actions. There's 5D superangles, including a fluid flying tower. There's Chanton's got a mixed 5D 60 action, and also a nice story where you enhance the gauge group to get the self-duality action. And then there's a non-local 60 action of these authors. And actually, I forgot, rather than Kim Young Lee has got a thing where he compactifies on the twist. It's a lot like this story, the previous story. I should have written that. I apologize to him, where he gets a Chern-Simons level theory because he's reducing on a CP. He takes S5 and he writes it as a CP S1 over CP2, and then he gets a nice action there. So I shouldn't do it. Okay, let me now talk about more hopeful things, or what could we do, or is there anything to know? So, one might expect relations between M2s and M5s. Certainly in string theory, the D-branes are all related to each other by T-duality, and you can trivially map between their Lagrangians. There is a T-duality in M theory, and Hirschman mentioned it. I assume this is what he was talking about. It's inherited because you just take a 3 torus, and you go down on one circle to 2A, T-dualized to type 2B in the second, T-dualized back on the third, and then lift back to M theory. And indeed, this T-duality on T3, if you wrap M5s, you get M2's orthogonal to it. And M2's orthogonal to T3 give M5s on T3. So that's the symmetry of the full M theory. The problem is you need to take a decoupling limit to talk about the field theories. And that requires taking the radii to 0. Get rid of the k nodes, which would be bank size k nodes. But that does give you 2 relations. First is actually rather trivial. In other words, M5s on a T3 of vanishing size gives you M2s orthogonal to R8 in the limit that R goes to 0. And the dual torus, which is going to inverse radius. Well, that's rather trivial, because you take the M5 brane on T3, well, that's your 3D maximum superspectral J mills. Shrinking torus makes you go to strong coupling, so it's just saying that the M2 branes are the strong coupling limit of 3D super mills, and you knew that. So this is rather trivial. The second one is rather tricky. I tried it in this paper, and I encourage someone else to try it. You should be able to construct M5 branes by taking parallel arrays of M2 branes and shrinking that circle, shrinking the transverse space. That's what this says. And then all the winding modes of the M5, of M2s, should reproduce a cruiser-time tower on M5 brane. We tried it, and we were partly successful. But I won't go into the details of read this paper. We gave a modified version of 5D superangles. Why is it hard? It's hard precisely because we don't have that translational variance in the GM action. So how do you construct a periodic array that you need to? It's non-perturbative. Anyway, okay. Another one would be a flux background. M2 branes in the background 3 form expand to M5 branes in a Myers type effect on a 3 sphere. So a while ago, popular Jackson Stars, they constructed the effective action from ABGM, and again they just found 5D superangles. Although we wrote a paper, I wrote a paper then following up saying, look, you can actually map the role of the monopole operators in ABJM as creating momentum modes in 11 dimensions. They simply map to Wheeling-Colvin instanton operators, but they are replaced by instanton effects in this case theory. You can map between them. And the last one I want to mention, that I think is cute, and I don't quite know where it's gone or where it's going, is that it was noticed long ago by these authors and improved on by these authors. That if you take BLG with a Nambu bracket, it's an infinite dimensional tree algebra, where you take x, y, z functions on some auxiliary three manifold, and you construct a Nambu bracket, then the BLG Lagrangian turns into a abelian M5 brane. Don't quite know why, but it does. And how it works, I don't quite know, but there's hope that one could do something there. Okay, I've got 1 minute.
Yeah, 2 minutes.
Okay, 1 minute. Challenges wish list. Okay. Provide a field theory definition without recourse to string theory. Because it should be something you can take to your colleagues in a different department and say, look, this should exist. And we know how to do it. What's of relevance to this conference, of course, is what are the structures? How are you going to capture things? One thing I haven't mentioned at all is the fact that there's apparently a two-form in the 2,0 theory, which is non-abelian. And you need to have a notion of what the periods of that thing are. These are the Wilson lines, well, they give you Wilson surfaces. And I know that there's this E2 group story, which I'm just not going to say anything more because there are real experts in this room about it, which addresses this issue. And I think this is something that presumably the whole conference is interested in. What is the mathematical language? How do we do things really in six-dimensional sense? And that's what we're saying here. We'd like calculable formulations of 2,0 theory with six-dimensional diffeomorphisms and relativity. Ideally, that's the ideal. This is the wish list. An action. I spent some time dismissing actions, but we all agreed that there's always a wiggle room, and you should take those lessons. So construction action and partition functions, it's not thought as a single partition function. Families or actions is another way, like, look, that's the approach I have these days. Well, in this case, it's described by that action, in this case, it's described by that action, but it's not single actions. Better understand the quantum operators, such as monopole operators and instanton operators, because one of the lessons, I think, from the M2's is that you need those things to fully understand theory. One of the goals, holy grail of this whole story is that S-bar is supposed to be manifest. So is there a formulation that does this, and this relates to this existence of diffeomorphism. And again, this famous NQ behavior, maybe you want to make that manifest, although maybe not. I mean, in the M2 brane story, it's also not manifest. That's actually shown by Marinho and Drucker that you get this n to the 3 halves. It just comes out of a localization calculation. No one's found an intuitive way to understand that, so maybe that's not the right question here either. I now begin my research talk. Do these equations mean anything to anyone? Thank you. I would be very happy if anyone's interested to talk to me later. So I've got a 2,0 system which I've worked out. This is the algebra. It involves this same triple product that appears in BLG. It's a system, these are the equations, these are the symmetries, these are the equations of motion that come from closing the algebra. There's a bunch of constraints. Yeah. You solve the constraints, and this theory spits out equations of motions. Those equations of motions come from actions, and you get BLG, you'll get 5D supernull, and then you get null versions of those as well, which are new. I won't go through it all. But you do get these weird actions like this, which are not Lorentz invariant, but they have maximal supersymmetry, and their equations of motions give you this motion on moduli space of instants.
So that you have an action, but for the null case, is that what you're saying?
Yeah, so this one, for example. So this has got x plus is like time. So you see you have an electric field, but no magnetic field. You have no time derivative on the scalar. This is the Lagrange multiplying constraint imposing self-duality of f, and then the fermion. This has got 16 supersymmetries.
That's the thing with fixed light momentum.
Well, that's its interpretation, yes. Its interpretation, this is an action for the DLCQ. So it gives you the equations of motion for this, all the action.
But it doesn't reduce it to this DLC quantum mechanics.
Yes, it does.
It does.
That's what it is. It's a field theory lift of it, if you like. But it has 16 supersymmetries, unlike 8 that you see. And then there's an even wackier one for the M2 brane. Here, this is all fermions, but you get a weird term like that. It's a thing of great beauty. If you've got time derivatives on Z, but no time derivatives of X, there's a Lagrange multiplier imposing homomorphicity. What's neat to me is these all arise from the freeform. H is part of the freeform, and this G is part of the M3 freeform. Anyway, I'd be happy to talk if anyone has a sense of that. Why? And why do I think this audience might know about all this? Is what it's got a bunch of fields, and I really apologize for screwing up your coffee breaks. You've got position coordinates, and these y's that feed into this are like winding coordinates. So if y takes a vev, then it's the M5 brane wrapped on the direction y. But then on the TDO picture that's in codes, y becomes position coordinates for the M2 brane. So this stinks of double field theory type stuff, and there's a constraint, which is like a section condition. So my question really is, does this mean anything to you? Okay, thank you very much.
Thank you. Maybe one or two short questions.
I have a question regarding the issue of whether there can be more supersymmetries than are manifest.
Yes.
So there's a classification of the supergravity backgrounds of the form AS4 times compact that reverse the supersymmetry by Figueroa or Farrell. And it says that the only choices are the compact spaces S if you want to reverse some supersymmetry. It's S7, mod some finite group, and then it gives a list that starts out looking just like your list. So it says for Z mod 2 you get n equals 8, for Z greater than 2 you get n equals 6, and then for the dihedral blah 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 groups it gets n equals 5 and n equals 4. So that seems to say, that for mod Z mod k you do just get n equals 6, not n equals 8 unless k equals 2.
Yeah.
On the supergravity.
Right.
Wouldn't that, maybe not full proof, but that seems to suggest that there's no more supersymmetry than is manifest in the ABJM model.
I'm not saying that there's more supersymmetry in the ABJM theories than we know about. No. If you can go to the dual, gravity dual, then I think that will give you the right answer.
Yeah.
So the point is, if you look at when I said manifest, if you look at ABJM, k equals 2, k equals 1, the supersymmetry is not a variation of the Lagrange.
Okay.
It's a conserved current that you can construct in the Hamiltonian formulation if you wish, but it is not a Noether current. It's like a, well, it's not a good analogy, perhaps. The Kepler problem has an SO4 symmetry, right? SO3 is realized by a Noether current. The other SO3 is by the Runge-Lenz vector, and you only see it in the Hamiltonian formulation. These theories, ABJM has 12 supersymmetries that are symmetries of the infinitesimal variations of the fields in Lagrange. That never changes. What changes is that k equals 1 or 2, there are additional symmetries, conserved currents, which exist in the quantum theory.
But I was thinking that you said it was kind of open whether for k greater than 2 there could still be something.
No, I didn't mean to imply that. The lesson I was trying to suggest, what I was trying to feed forward was maybe when we're looking at the M5 grade, you should keep an open mind. And there could be symmetry, and not look for theories of supersymmetry. Or maximal supersymmetry. I mean, people often try that, they just do one.
Okay, so maybe the discussion can continue. Well,